stop to think about the hidden science sitting right there in your medicine cabinet? You know, that little bit of magic that makes a cream feel just right or keeps a liquid medicine perfectly mixed? Well, today, we're going to pull back the curtain on the fascinating science that controls how your medicine squeezes, spreads, and most importantly, how well it actually works. It has a name, and it's called rheology. So let's just jump right into the heart of it with a question you've probably never thought to ask. Why is it that a thick ointment will just sit in its tube, totally defying gravity, but the second you squeeze it out, it spreads under your skin like silk? The answer to that is a science called rheology. And trust me, it's the secret ingredient behind almost every cream, gel, and suspension you've ever used. So here's our game plan for this explainer. We'll start with the science of flow itself. Then we'll check out the simple Newtonian standard before diving into the much more common and way more interesting non-Newtonian world. We'll uncover the magic of a property called Viscosity, and finally, we'll connect it all back to your local pharmacy shelf. All right, first up, the science of flow. At its core, this is all about understanding how different materials, we're talking everything from water to those super thick pastes, move and change shape when we push them, pull them, or spread them around. The official name for this field is rheology. It's a cool word, right? It comes from the Greek word rheo, which literally just means to flow. And it's the fundamental science that governs, well, everything that flows, from the water in your glass to the fancy gel in your first aid kit. So why do we even care about all this? Well, because getting the flow just right is absolutely crucial for our medicines. It's what ensures a product stays stable on the shelf so the important bits don't separate. It controls how a drug gets released into your skin. It makes a cream easy to handle, and it even affects what they call patient acceptability. I mean, let's be real, if a cream feels gritty or runny, you're not going to want to use it, are you? All of this directly impacts how effective the medicine is in the end. Now, to really appreciate the clever science going into our medicine, we first need to establish a baseline. And that brings us to Section 2, the Newtonian standard. Just think of this as the simple, predictable, by-the-book rule for how fluids are supposed to act. So, an ideal fluid, what we call a Newtonian fluid, follows one very simple rule, Newton's law of viscosity. All that means is the relationship between how hard you stir it and how fast it flows is perfectly consistent. No surprises. And this graph shows it perfectly. It's not as complicated as it looks, I promise. On the bottom axis, you've got shear rate. That's just a fancy way of saying how fast you're stirring. On the side, shear stress. That's how much force you're using to stir. For a simple Newtonian fluid like water, you get this perfect straight line. Its viscosity or its thickness never changes. Stir it fast, stir it slow, water is always, well, water. But here's the big twist. Most of the stuff in your medicine cabinet, they're not simple and predictable at all. And this brings us to the non-Newtonian world, which is where the rules of flow get really interesting. This chart just nails the difference. Newtonian fluids, they obey the law, their viscosity is constant. Simple. But non-Newtonian fluids, they're the rebels. They break the law. Their viscosity actually changes depending on how much force you apply. They're complex, they have an internal structure, and that is exactly what scientists want to work with. And these little lawbreakers come in a few different flavors. So let's explore the three main types of non-Newtonian flow that, believe it or not, you probably use every single day. First up, we have pseudoplastic behavior, or as it's more commonly known, shear thinning. This is when a product gets thinner the more you stir it or spread it. So why does that happen? Well, inside you've got these long polymer chains that are all tangled up. But when you apply force, they untangle and line up, which reduces the resistance. For pharmaceuticals, this is basically the holy grail. It lets a product stay nice and thick in the jar, but spread on your skin with zero effort. Then you've got the total opposite, dilatant or shear thickening flow. This is where a product gets thicker the more you mess with it. Imagine a really concentrated paste. As you try to stir it, the particles all jam together and fight back. As you can probably guess, this is pretty much the last thing you want in a medicine. It makes manufacturing and applying it a nightmare. And our third type is plastic flow, which introduces this really critical idea, the yield value. A product with plastic flow basically acts like a solid until you apply enough force to cross that threshold. It needs that initial oomph to get moving. And this, right here, is the secret behind our original question. It's the reason your toothpaste and ointments stay perfectly put in the tube, just waiting for you to give them that decisive squeeze. So all of this brings us to the most elegant concept of all. Let's talk about the genuine magic of thixotropy. This is the property that really gives pharmaceutical formulators the absolute best of both worlds. So, what in the world is thixotropy? Okay, it's a behavior that's all about time. When you shake or stir a thixotropic fluid, its viscosity drops, it gets thin. But here's the key, that change is reversible. When you let it rest, it slowly rebuilds its structure and gets thick again. It's almost like the fluid has a memory of being disturbed. So cool. Let's just walk through this cycle. First, when it's at rest on the shelf, the product is a nice, thick, stable gel. Nothing is separating or settling out. Then you shake it. The internal structure breaks down and boom, it becomes a free-flowing liquid that's easy to pour. And finally, once you've applied it and it's at rest again, it slowly rebuilds that gel structure to stay exactly where you need it to be. And it is no exaggeration to say that this is what the scientists are aiming for. As our source material puts it, thixotropy is a highly desirable property in many pharmaceutical formulations. It's the absolute key to making a product that is both stable on the shelf and a breeze to use. Okay, so let's tie this all together in our final section, from the lab to the pharmacy. This is where we really see why this hidden science matters so much to your health and, honestly, your comfort. So here's the bottom line. Rheology is this incredible, unseen force that just makes modern medicine work better. It ensures stability, so the active ingredients don't just sink to the bottom of the bottle. It guarantees you get an accurate dose every single time. It's responsible for creating those smooth, elegant textures that make a product feel good to use. And maybe most crucially, by controlling the flow, it can control the drug release, making sure the medicine stays put and works for longer. So the next time you squeeze a tube of ointment or shake up a bottle of calamine lotion or spread a cream on your skin, just take a second. You're not just using a product, you're actually interacting with a tiny masterpiece of physical chemistry. And now you can ask yourself, what hidden science of flow can you see at work?